In this next part of section 13, we're going to be looking at factoring polynomials. Factoring polynomials is a skill that I expect all of my students to have coming into a college algebra course. But there are a variety of factoring techniques that one is taught over their career in math, and sometimes we forget some of those details. So I'd like to take the time with example 13.4 to briefly review some of these different factoring techniques that we'll be using on a regular to semi-regular basis here in college algebra. So we're going to start with part A, and actually before I get with part A, make sure that we read the instructions. It says completely factor. Now that's a really important thing for us to see, because oftentimes you're taught factoring in isolation. You just learn about one technique at a time, and it's the synthesis of putting all these different factoring techniques together that makes factoring such a powerful tool. So here we are going to be asked to not just do one particular factoring technique, but just completely factor to the extent of what we can with today's knowledge. So as I'm going through these, I'm going to indicate what factoring technique I'm using. So for part A, I have f of x equals 3x to the 4 minus 48x squared. I will always start by looking for a GCF every single time. Every single polynomial has a GCF. Sometimes the GCF is just 1. That's the only thing that they share in common. It's just a factor of 1. If the GCF is just 1, then I don't do anything with the GCF, because that's a pretty insignificant greatest common factor. But if the greatest common factor is anything other than 1, then that's where I will start with my factoring process. I will always do that. So this one does have a greatest common factor other than 1. So we have f of x equals, and I'm going to pull out 3x squared, and that's going to leave me with x squared minus 16. So as I mentioned, we need to make sure that we completely factor. We're not just trying to do one technique and then be done. We want to get it completely factored as far as we possibly can. So there is another technique here. Again, what we just did was GCF, greatest common factoring. But the next thing that I want to introduce is, not introduce, but review, is the difference of two squares factoring technique. Difference of two squares. So the idea behind the difference of two squares is relatively simple. I'm going to take a number, and I'm going to take another number, and I'm going to square each of them, and then I'm going to subtract. Hence the name difference of two squares. Okay, so the name gives away a lot of what it is that the technique is supposed to be applying to. The pattern is that you will take the two numbers, a and b, and you'll subtract them to form one factor, and then you'll take the same two numbers, a and b, and you'll add them together to form a second factor. And this is the pattern that is difference of two squares. So this brings up an important question. How does this actually apply to what we're dealing with here? So inside my parentheses, I have x squared minus 16. And x squared minus 16 can really be thought of as x squared minus 4 squared. So if I do that, then that would mean that the x is analogous to the a, and then 4 would be analogous to the b. So in my factoring pattern, everywhere that I see a, I'm going to replace it with an x. Everywhere that I see a b, I'm going to end up replacing that with a 4. That's how this process works. So we would have f of x equals 3x squared times x minus 4 times x plus 4. And that would get us the complete factoring for this function. Now I don't want to stop here. I would like to also go back and look at an interesting connection with the concept of degree. So looking at the standard form equation that we were given, I would say that the degree of this function is equal to 4, and I can base that off of the leading term here. There's the highest power of 4. That's how you identify degree when you're in standard form, by looking at the leading term. When you are in factored form, the factored form is supposed to be equivalent to standard form. It's just a different form. So that means that the degree of the polynomial should not change just because we've gone into a different form. And it doesn't. Here's how you can find it. If you look at, let's say, the first factor here, 3x squared, that would be a degree 2 factor. If I look at x minus 4, that would be a linear degree 1 factor. X plus 4 also is a degree 1 linear factor. And if you add all the different degrees up from your factors, they will end up equaling 4, which matches the degree that we come up with from standard form. So that becomes really powerful for when you're trying to identify the degree of a polynomial. If it's in factored form, you don't have to necessarily multiply it out into standard form to achieve that goal.